Thank you all for joining. We're very excited to share this work with you. GlobalConfusion, TrustZone, Trusted Application Audits by Design. This is joint work of Philipp and I. We're with the HackSive, led by Matthias Paya, who's a professor at EPFL. This is actually kind of the summary of some academic work that has been published at Usenix Security, which is one of our flagship venues in academia for systems and software security. Hence these kind of artifact evaluation badges that you see in the upper right here. So all of the stuff we're presenting here should be available online. And if you want to dig deeper into it, feel free to check out our papers and code. So with that, let's dive into this. I'm going to give you a little bit of a teaser. In 2016, there was an event called GeekPwn in China. Some of you might be familiar. And this guy here managed to compromise a phone by the Chinese phone manufacturer Huawei. And this was like a very interesting exploit chain affecting the trusted execution environment in the end. And he made an audience member unlock the phone with her nose. So this was very kind of interesting to see from how they medially prepared all of this. So it turns out that the vulnerability that was used here as part of an exploit chain not only affected this one vendor, Huawei, but also a couple of others, like Samsung a little bit later. This was 2019. And as you can see from the severity on this SVE, which is, Samsung's internal vulnerability enumeration, it's critical. And Samsung has always been public about their vulnerabilities, and there was not only one, but actually a couple, kind of the same thing over and over again. And then later, by these guys here from Realize, they also found the same vulnerability pattern on their TVs. And a little bit later at DEF CON, there was this guy here who also found it in Xiaomi devices. So there's something affecting trusted execution environments that is kind of a pattern that keeps on reappearing. And in this talk, you will get to know what's actually behind all of this. So just a short introduction. Who are we? So Marcel and Philipp. I'm a postdoc with the hack side at EPFL. Philipp is a PhD. We're both interested in kind of embedded and mobile security, Android in particular, Android trusted execution environments, fuzzing, and kind of vulnerability research in general. So to get us all on the same page, just a little bit introduction, like trusted execution environments on mobile devices. So we're running a bunch of apps on our devices. They process sensitive information, and we have a bunch of kind of like threats, right? Malicious applications being installed or your phone being stolen. And as a second line of defense, vendors came up with this idea of a second isolated execution context, which kind of hosts some modules responsible for some of the most critical features, like biometric authentication or the cryptographic key management in general. And typically, mobile devices run on ARM, and that the technology to build a trusted execution environment here is typically ARM TrustZone. And this is what this talk is mostly going to be about. So it's not only mobile devices, but a whole range of devices that actually rely on primitives given by the trusted execution environment. You might be familiar with your phone and your tablet. You might be familiar with your TV running this software stack, but basically also your smart home hub, your infotainment system in your car, your Starlink user terminal, and your favorite drone might also run a software stack which resembles what we're going to show in this presentation. So a little bit of a motivation. So I think the BlackAlps crowd here is a bit diverse. Why should you care? I brought you two kind of lines that might motivate you. So maybe you're part of a red team or a blue team or somehow like a third-party auditor, and the product you're reviewing is undergoing some sort of certification, like the common criteria, right? It's a typical thing you do. And yeah, as Samsung did on this slide here, the trusted execution environment would probably be part of your evaluation target, right? So this might be of interest. from this perspective, or you're more motivated by money, right? And in the back, you see like a pwned infotainment system that is running a trusted execution environment during pwn-to-own automotive beginning of this year. And in the front, like the up to bug bounty amounts that Google is paying when you pwn their trusted execution environment, which is really hard, but also rewarding. So no matter where you're coming from with your motivation, now we're going to go a little bit deeper into the technical details. What you will see on these ARM chips, plus the Cortex-A, the application profile chips, is this world split, okay? Where on the one side, you have this thing called the normal world running your Linux kernel typically, right? And on top of that, a couple of applications. For the sake of this presentation, it's the client applications because they are client to the trusted execution environment, which is typically referred to as the secure world execution context. And here you have another operating system, actually, which some apps called trusted applications, since it's the secure world, are running on top of, right? And the client applications make use of these features that I've been talking about before, like cryptographic key management or biometric authentication, for example. So now, very interesting, these operating systems are kind of isolated from each other, meaning they have different views on their interpretation of memory, right? So they're hosting their own page tables, and they kind of don't know much about each other, and they need to communicate with each other to exchange this information, right? So, and information is typically passed from client applications to trusted applications via this logical channel, and the operating systems beneath need to agree on a common view of memory, right? They share information using some shared memory infrastructure. And you will later see that this agreement of how to look at this shared memory can be problematic. But before we go into this, there's another thing I wanted to talk about on the slide here, which is Global Platform, which is this institution which tries to bring like a little bit of a standardization into this like organically growing mess that you see in trusted execution environment. And Global Platform sets out to like specify some of the commonly used APIs that you will see in this context. And one of these specifications is the TE internal core API, which is basically defining how do trusted applications talk to the trusted operating system, and how are they interfaced from the outside world. So when a client application talks to a trusted application, you will find how this is supposed to work according to Global Platform in these specifications. You can find those online. Those are a couple of like 100 pages at most, I guess, specifications that define how this looks like. And we will go a little bit deeper into this specific specification here and looking at one of the defined APIs, which is this one. Don't be scared. It's a lot of C code. I'm just going to walk you through this briefly. So we're looking at a function. You can see the signature here, the TA invoke command entry point. And the first argument here is a like void pointer to some object that is supposed to store session-related state. Like in the context of this talk, we're not too much interested in that. Then we have an ID for a command to kind of select what kind of action we want the trusted application to do, to select the right command handler. Then we have another parameter which determines the types of the next parameter, which is an array of parameters. Okay? And the underlying structure for the elements in this array is shown here on the right. That is a union. Okay? So in this array, you have 4 unions, and each of these unions are these structs. And when you have been paying attention to your C class in school, you know that these structs in memory, since they are defined as a union, overlap in memory, right? So on a 32-bit system, this void pointer buffer would overlap perfectly with this UN32A, and the size will overlap perfectly with the B value in the value member of this union. Okay? So as I said before, the param types parameter determines the type that this function in the end sees, right? And you can already kind of spot where this entire flaw is going to. Because I was telling you that these two worlds need to agree on a view of memory, right? So and when I send like a memory reference and indicate it as such to the trusted application, the trusted operating system needs to take care of taking this reference and map it accordingly to the virtual address space of the trusted application, right? So now we can think about situations where that might go wrong. So we go further through this code. So first, the specification says, well, you should really check these types when you write a function like this, and that's typically what you do. You define the expected types and then compare it, and you error out if you don't see the expected types. And the rest of the code here just demonstrate like a very simple example where you have two parameters. One is an input buffer, the other one is an output buffer, and you're just copying the bytes from the one buffer into the other. Just an echo trusted application as a demo, right? So unfortunately, this check up here where you are checking your parameter types is optional, right? So it will work perfectly fine if you just forget this check, right? And as you know, when you're developing things and they just work out of the box, like why would you touch it again and change it? You wouldn't even recognize that it is actually broken. So and the crux comes into play when you now pass a parameter that is interpreted by the trusted application as a memory reference, as a value, because then it does not undergo this kind of sanitization and virtual memory mapping that the operating system does to modify the trusted application virtual address space, right? So you get like a raw, you get control over a raw pointer in the context of this trusted application, meaning that the memmove operation down here will give you like an arbitrary write and an arbitrary read immediately when you're malicious and just try to exploit it in the context of this trusted application. Okay, so that is the problem, and we think this is kind of a weak design to leave it kind of fail open, we say, right? When things just work, but like security is not enforced, it does not fail safe. Okay. So with this in mind, we go further, and we were wondering during our research, okay, this seems to be a thing that will be done wrong all over the place, and I already teased you that it has been done wrong, and we wanted to know like how often people actually screwed this up. So we did a prevalence study on this. So we assembled a data set, looked at the 5 top Android phone vendors according to market share, which corresponds to like a 65% market share, some 500 something firmware images, it's like terabytes of firmware images, like 54 devices we were targeting, and 5 different TE implementations over a time span from 2016 to 2024. We looked at like about 14,000 proprietary trusted applications. There are like duplicates in there and different versions of the same trusted application, and it boils down to like 340 unique kind of trusted applications. And we did some advanced static analysis, right? grep to the rescue. With this one-liner here, you can earn a lot of bug bounty money. So what we basically did, we took all of these trusted applications, took our decompiler of choice, got the decompilation, and if you just kind of at least name the variables in the signature, which are known because you have access to the specification, right? You can just do a grep. And if param types only appears once, right, it's probably broken. So, and this was our first attempt to do like a static analysis to do this. We found a couple of instances using this. But then it turns out life is not as easy, and this research project continued. So we looked at some more examples, and those are illustrations to kind of tell you, hey, it's a little bit harder. So here, a little bit of C code to show you, well, we kind of start with this params array. We're passing it down to this vulnerable function here. Here it's the parameter of this function, and then there's a use, and the parameter types, as you can see here, forwarded into this functions are not checked in this function, okay? But this is not the case that we're interested in. I mean, it's not checked, right? But just the usage of a value is not very interesting from like a security standpoint, right? You don't gain any control over pointers in this scenario. To contrast this with the other scenario where, again, you have the params array passed down to the vulnerable function, consumed by the vulnerable function, and then there's actually a buffer being used, load and stored from. Then we check the param types down to this function, and they're not checked. So this one here is much more interesting. So as an exploitation primitive, it's probably not very useful, but it exemplifies the point that we are interested in parameter memory references being dereferenced at some point in time using load or store operations to memory. So and what you do, we wrote a tool called GP check, so global platform check, if you will, based on Ghidra. And what we do is do like a typical static analysis. We generate the interprocedural control flow graph, as you can see here on the right. It's a little bit simplified. Then you do something which is called like a def use information flow analysis. So you kind of track the definitions of the parameters first, the use here when we pass it down to the vulnerable function, another definition when it actually arrives inside of the function. Then we have another use. This use is actually getting the member in this struct that we're interested in, which is this buffer. Then we trace this buffer throughout the execution and see if there are any stores or loads to this pointer. And this is actually happening here. And the other thing that we look for is the parameter types, which we also track down into this function. And we see there's no usage. And then it's an easy kind of graph reachability problem along the edges of this control flow graph, where you just see, okay, from the start, from the invoke command entry point down to the usage where an actual load to attacker controlled values is happening, there's no sanitization happening on this way, right? So we never check the types along this path. And this is kind of the alerting condition we look for in our static analysis. So we use this, okay. First, the summary of this checker. So it's Ghidra based. You can use it on production trusted applications, so binaries, and it's open source. Feel free to go through our Python code that implements this analysis. And yeah, there's this overview of how roughly the logical components look like. So the results of this, from this initial set of trusted applications, we found that approximately 60,900 were actually global platform compliant. That's around 130 of these unique without duplicates. And 850 of those were actually vulnerable. That boils down to 33 unique vulnerable trusted applications. So 9 of those were actually publicly known. So we found advisories which corresponded to what we saw in our reports. 10 of these were actually silently fixed. So the vendor never disclosed anything about that there was something wrong with their trust applications. And we found 14 O-days that we responsibly disclosed. And Xiaomi and MediaTek and Samsung and everyone affected by now hopefully fixed everything. We got a bunch of CVEs assigned and like a comparably low amount of bug bounty money that our research institution happily invests to do more fancy research. So with that, there's a little bit of a timeline to just give you an overview that this is a vulnerability pattern that happened over and over again, right? In the beginning, I showed you this GeekPwn instance. Then Samsung kind of found a couple of instances here, like a batch, and they kept on finding things. Then Xiaomi found something a little bit more, Oppo and Vivo, and then Huawei again, and then like our research kind of disclosed 14 of them. So you can see over the years, this has really been an issue in these trusted execution environments. So instead of just attacking things, we sometimes also repair things, and we suggested a mitigation, which is currently work in progress, to a global platform to kind of change the standard to enforce this type check for developers, right? Which basically makes it mandatory for developers to first define which command IDs correspond to which types, and only then you can actually invoke the trusted application and make use of these parameters. So we built a prototype on top of Opti, which is an open source reference implementation for TrustZone-based trusted execution environments. And you can check out our code in the repository. So this, like changing a specification usually takes some time, right? This is why we also reached out to the Opti developers themselves. This is, I think, the one kind of publicly facing TE implementation that we have. And Joachim Bech was friendly enough to add this little warning here for all the developers who are facing this and kind of pointed to our research and say, hey, you should really, really, really check your types, right? So that was the GlobalConfusion part of this, but this is not the end of this talk. We're going to spill some more tea, which goes into the following topic. So trusted applications are these little kind of loadable blobs, right? So you load from your rich operating system into the trust execution environment. So they're like binaries that are signed, and only those that are correctly signed are accepted by the trusted execution environment. So now we found a bunch of vulnerabilities in these trusted applications, which are like to a large degree easily exploitable, right? With the read and write primitives that we saw. So now the vendor goes along and patches these trusted applications, and there's two versions existing now, right? You can just grab an old firmware image and get the properly signed version of that and just load this one into the trusted execution environment, and you have your control again. And that's called a rollback attack, right? And vendors should, of course, like all across the board, take care that this cannot happen. And the mechanism to do that is typically the trusted application header has a field called the version counter. And when you load a trust application into the TE, the loader will look at this version. If it's a new version, it will update the last seen version and will only accept versions that are equal or greater than the version it has seen last, right? So that it will exclude vulnerable and outdated trust applications to be loaded to prevent rollback attacks. Now, Project Zero looked at this already in 2017, right? And for sure, during these, 7 years that have passed, a lot probably has happened in the industry and everyone is protected against rollback. This is why we ventured out to do another empirical study to see if this feature is actually supported across the ecosystem. So again, we built up an analysis pipeline, collected a bunch of firmware images, and we built some parsers for trusted applications to figure out the rollback counter like representation in the headers. And we also built this repository, this collection of vulnerable trusted applications to kind of see, hey, when there is actually a public advisory for a vulnerability, there should for sure be a rollback counter increase, right? So again, covered a bunch of firmware and OEMs that is on the market. Ended up with 35,000 trust applications. Only 4 TEs here. We saw 190 usages of this rollback counter all across the board. And our collection of vulnerable trust applications, not only the type confusion bugs, but also all the others we found, it's like around 2,500 vulnerabilities. So and it's kind of surprising, or not so much, to see that so in these trust applications, the whole set, we see that 2,500 of them are vulnerable, and you would expect that out of these 2,500, there would at least be one rollback counter change for each of them, right? That's not the case. So we only see 190 rollback counter changes, which will not cover all of the rollback cases that we need to actually prevent rollback in the ecosystem. So to like sum this up, it's basically rollback counters are not used, at least not by large parts of the market. Even when publicly known vulnerabilities with more or less like copy-paste, like weaponized exploits are available from random GitHub repositories. From 51 devices we looked at, like 29 had at least one trusted application where we could perform a rollback attack. And only Samsung on the newest flagship phones was one of the vendors who kind of did something about rollback attacks. So this is a little bit more detail about the analysis we did. What the slide is showing you is one device. On the left you see all the trust applications, or like a subset of the trust applications that are deployed there, and we tracked the firmware images over time, and each of these lines shows you like events that kind of changed something about the trusted, this specific trusted application. So here this little X kind of shows you, hey, there's a vulnerable version introduced. The rectangle kind of shows you there's an advisory, a public advisory. And you would expect that a rollback counter change would happen right after, but it's not. And for this specific case, there's no rollback counter change up until the end of our analysis phase. And for many other devices, you will find a lot of more details in our academic paper that you can follow here with this QR code. And with that, we're at the end of the kind of conceptual part. Now all of your teapots are probably burning, and Philipp will go into a little bit more practical demos to show you how this actually looks like on a real device.
All right, so in this part, I'll walk you through the finer details of actually carrying out a rollback attack and triggering these type confusion bugs on real devices. Why do we do this? Because basically all of the findings that we presented before, basically found them by just statically looking at firmware, but we kind of want to make sure that the findings we present are actually real. And the way we do this is we trigger this stuff on real devices. So we took a bunch of phones, Samsung and Xiaomi phones, with a nice range of different system-on-chip and TE implementations, and we routed all of them to sort of simulate a compromised rich execution environment or normal world. You might be wondering, okay, your root, isn't this all over? No, because that's the whole point of having a trusted execution environment. It should, like the data that's in the trusted execution environment should still be protected even against like a fully compromised normal world, which is essentially root. And I will walk you through, or the rolling example is going to be the Xiaomi Redmi Note 12, where I'll show you in detail how to do a rollback attack and how to trigger the type confusion bug. But the steps to do it is sort of equivalent on all the other phones. All right. So our target is the Xiaomi Redmi Note 12, and the target trusted application that we want to roll back is the key install trusted application. It has this name 0811 whatever, and we want to roll back to a version from the beginning of 2023. Why the beginning of 2023? Because during 2023 we found and disclosed a type confusion bug inside of that key install TA, and sometime in November this was fixed. And the target phone, so our Xiaomi Redmi Note 12, is running HyperOS from August 2024, which of course ships a fixed version of the key install TA. But, well, a fixed version of the key install TA is not interesting to us. We want to trigger the type confusion bug. So that's the perfect case to actually carry out the rollback attack to make this sort of up-to-date Xiaomi Redmi Note 12 load our vulnerable key install trusted application. How do we do that? Actually, it's pretty straightforward. First off, you download a firmware version for this phone from 2023. You extract the vulnerable key install trusted application, and then there's just 3 shell commands. You upload the vulnerable key install TA to the phone. You remount the vendor partition as writable, and then you essentially overwrite the existing, sort of the fixed key install trusted application that's deployed on there with the outdated and vulnerable one. And now when the trusted execution environment goes, and this path here, this vendor THHTA, this is the path where the trusted execution environment loads the trusted applications. And so we've replaced the existing fixed key install TA with the vulnerable key install TA, and the trusted execution environment will go in and load our vulnerable and outdated key install TA. Why does this work? Because the outdated and vulnerable key install TA is still correctly signed, and between the beginning of 2023, sort of the outdated key install version, and August 2024, there was no rollback counter increase. So that's rollback. So now we have a way to make the TE load our vulnerable key install trusted application. Now we want to go in there and actually trigger the type confusion bug. How do we do that? Essentially what we need to do is we need to write our own client application. So that is just a user space program running in the normal world, so in the rich execution environment. It's just a bunch of C code where you essentially use the global platform client APIs with sort of this library, or usually you'll have a library that's deployed on the phone that essentially takes care of setting up the communication to the trusted execution environment. And, well, in order to communicate with our rolled back key install trusted application, what we need to do is we need to open a session to that key install trusted application. This is this TEC open session function down here. And the relevant parameter is the UID, which we derive from the name of the key install trusted application. And when we call this function, what happens in the background is the trusted execution environment goes and loads our outdated and vulnerable key install trusted application, and then opens a communication channel between our client application and the now loaded into the TE, the vulnerable and outdated key install trusted application. And now we can basically call into this trusted application, and we can call the TA invoke command entry point function that you saw in the beginning using this TEC invoke command function sort of from the client. And what we're doing is we're essentially just calling this function with this TEC operation parameter, and this parameter holds like two fields, the parameter types. So this is essentially for the 4 params in this params array. For each one, it basically tells the TA what is the type of that parameter. So here we say the first entry is a value, all the other ones are not set. And then for the first entry in the params array, we set it's a value, and we set the A member of that value to 10. And now, if we run our client application, if we run this on the phone without rolling the key install TA back, nothing happens. Well, the only thing that happens is there's a kernel log output saying bad parameter type. Why bad parameter type? Well, presumably, actually, when we make this invoke command function call, the trusted application is expecting a memref argument. But we're passing a value argument, and of course, in the fixed version, they will check the param types that we're passing, and they'll compare TEC value in out to memref. It doesn't match. We're not sending a memref, so the trusted application will just say, okay, no, you're trying to do something weird. I'll just go to an error condition, print out this error message, and exit early. If we run the same client application on the phone where we rolled the trusted application back, so we have loaded the vulnerable key install TA, what we see is we'll run the client application, and if we look at the kernel log output, there's a crash dump. So what happened? Well, the trusted application is expecting a memory reference. It's not checking the parameter types, and remember that in this params array, you have this union between memref and value. In this case, value.a exactly overlaps memref.buffer, so the pointer to the buffer. So the trusted application is essentially dereferenced a 10, expecting it to be a valid pointer, and of course, it crashed. And now we've rolled back a trusted application, and we've triggered the type confusion bug. And we did this for all the other phones. I showed you in a few slides before. But for the Xiaomi Redmi Note 12, we went a bit further, and we actually exploited or weaponized this bug to get code execution inside of the trusted execution environment. How do we do this? Well, to do this, we need to actually look at how does the trusted application handle our user input. So now we're looking at the vulnerable version of the key install trusted application. This is just an ELF file, so we're throwing it into Ghidra, and all the code that you're seeing in the upcoming slide is essentially just the decompiler window from Ghidra. And we're looking at the TA invoke command entry point function, where the command ID param3, which is the parameter types, and the parameters array is essentially our attacker-controlled input. And if we go down a bit further in this function is essentially a giant switch statement for the different command IDs. If we look at command ID 1, what happens is the trusted application first reads out the first and second entry of the params array. And then it prints out, it does this p input equals %p format string print to the kernel log. And it prints the first, so presumably it's expecting a memory reference because %p usually use that when you have a pointer. But the problem is the TA is not actually checking that we're passing a memref. So it could be, in this case, that TE param0 is memref.buffer, but it could also be value.a. Same for TE param2. Now this print is not super important, but these two parameters get passed into this function down here, this 97EC function. And in this 97EC function, so this code here is essentially just pseudocode that we wrote once we fully reverse engineered this function. What this function is essentially doing is it's reading from TE param0 or from key block, and it's writing to P outputs, so T param 2. And remember that we are in full control of both key block and P output. And if we send a value as P output, we can essentially set P output to an arbitrary pointer. And in the box outlined here, the trusted application writes an integer or 4 bytes into an offset of P output, which we fully control. And key ID is also read from the key block, which is also one of our input parameters. And we can set this to a valid memory reference and essentially fully control the value of key ID. So this is a fully controlled 4-byte arbitrary write using our parameter type confusion bug. And this is very convenient to exploit the phone because it turns out, so the Xiaomi Redmi Note 12 is a budget phone. And when you buy a budget phone, you get a poor man's trusted execution environment. What this means is there's no ASLR and no NX. And so if you have arbitrary write, exploitation is kind of trivial, except for the fact that the only way to debug is by looking at the kernel log output. So how do we exploit it? Well, we just write shellcode to a memory region that's writable and executable, and then we override a return address on the stack and jump there. And so I actually have a demo here. So this here is the Xiaomi Redmi Note 12, and I'll run the exploit now, and essentially, if it works, it should print out so when it works, our shellcode will essentially print out a banner to the kernel log output. So I'm just going to do this now. So here we're running our exploit. Now we're dumping the kernel log. And now scrolling up a bit, at this point here, we jump to our shellcode and we're printing out this nice little banner. And then down here, we just crash the TA. So nice. And okay. So at this point, you have like code execution. So let's say you have like these super powerful primitives, rollback and type confusion. And with those two, it's actually very feasible to get code execution inside of the trusted execution environment as a trusted application. At this point, though, you haven't like fully compromised the phone. You're essentially running in a user space in the secure world. If you want to fully compromise the secure world, you need to privilege escalate and actually pwn the trusted OS. But that's a story for like another talk, another day. We presented these two vulnerabilities, the prevalence of those and the exploitability of those, so rollback and the type confusion bug that affect all of the sort of modern Android smartphones. Thank you for your attention.
Amazing talk. Thank you, Marcel and Philipp. Very interesting. We have 3 or 4 minutes to take a few questions in the room. If there's anyone behind there can bring the mic. And Linus later.
Hello. Thank you for the great talk. It was very interesting. About the version counter, do vendors just revoke the signature of the vulnerable TA? Did that happen, or?
So the phones that we looked at, there was no change in signature, but this would be another like counter measure against rollback attacks. But we didn't see this in practice.
Okay, thank you.
There was another question here in the middle of the room. It was you, Linus? Yeah. Can you bring the mic, Nico? Yeah. Thank you.
Thank you all very much for the talk. Really interesting. Just so I understand correctly, to in fact exploit the downgrade, you need to have physical access to the device. So it's not sufficient to kind of install an application which does the downgrade and then uses the downgraded secure application to exploit the rest of the system.
So I mean, when you have a full chain in the rich OS, right, your root, you can kind of download an outdated version of the TA, put it at the place where it needs to be, and just run it. So like, you don't need to have physical access. You just need like a root shell, let's say.
But if you already have a root shell, don't you already have You don't have access to the trust zone.
That's
okay.
the point, yeah.
So you can go from the root shell to the trust zone.
Yeah.
Okay. Thank you very much.
Thank you. There, a last question maybe? No. So, can give an applause again. Thank you for your talk.